Okay, hi guys. So we'll be continuing on seeing more examples of writing Kp and Kc or Kpc for certain reactions. So in the previous reaction, we discussed that Ei would be nothing but Ri into I divided by C naught, where R was the activity coefficient. Again, this has no units. Okay, and we saw some of the examples on the same in the previous lecture. So let's see some more reactions. So we have HCN aqueous getting formed into H plus and Cn minus aqueous at equilibrium. So Kc would be nothing but H plus aqueous multiplied with Cn minus aqueous divided by HCN aqueous. Okay, so the unit would be mole per concentration or mole per liter, not concentration, mole per liter. Okay, and Kc naught would be H plus divided by concentration of H plus aqueous divided by C naught multiplied with concentration of Cn minus aqueous divided by Cn, this is curly brackets, divided by concentration of HCN aqueous divided by C naught. Again, this Kc naught would have no units, unlike Kc which had mole per liter. Okay, let's see another example wherein we have Zns plus 2H plus aqueous getting formed into H2G plus Zn plus 2 aqueous. So in this case, K equivalent again would be, so K equivalent as per thermodynamics we are calculating, so it would be activity of H2 multiplied with activity of Zn plus 2 divided by activity of H plus squared multiplied with activity of Zn. Okay, so for pure liquid, for pure solids and solvent, Azn activity is 1, so this would be 1. Okay, so I'm not explicitly writing it because I want to be as abstracted as possible in this example. And Kpc naught would be nothing but pressure of H2G divided by P naught, which is standard pressure. Okay, and multiplied with concentration of zinc plus 2 divided by C naught. Okay, then we divide this with concentration of H plus over C naught and square it. Okay, so now let's look at some basic concepts related to equilibrium constants. Basic concepts related to equilibrium constants. Okay, so let's first see the stoichiometric representation of chemical reaction. Representation of chemical reaction. So let's see some examples on the same. So example would be, we have H2G plus I2G forming 2HI again in gaseous phase. So Kp1 would be P of Hi squared divided by P of H2 into P of I2. we have Kp2s P of Hi, partial pressure of Hi to the power 4 divided by partial pressure of H2 squared and partial pressure of I2 squared. So which is basically K of P1 squared. Okay. So when will Kp2 come into the picture? So suppose we have 2 moles of H2G and 2 moles of I2G reacting to form 4 moles of HIG. So in that case, the equilibrium constant would be, or Kp2 would be defined as this, which is nothing but Kp1 squared. And suppose if we actually write this equation, H2G plus this was the original equation, I'm writing it again, gives 2 moles of HIG. So what happens if we actually balance the equation something like this? Then Kp3 would be coming out to be partial pressure of HIG divided by partial pressure of H2 G to the power half and partial pressure of I2 to the power half. Then it will be nothing but root of K of P1. Okay. So these are the various modes of representation of a equilibrium. Okay. So we'll see another example wherein, so these are all, first before writing the example, these are all modes of representation of equilibrium. Okay. Next example, let's see 2 moles of HIG converting into H2G plus I2G. Okay, so we just reverse the above reaction. So Kp4 in this case would be 1 upon Kp1. Why? Because Kp4 can be written as partial pressure of H2 multiplied by partial pressure of I2 divided by partial pressure of Hi squared. So this is nothing but 1 upon Kp1, or reverse of Kp1. Okay. Next, let's see another example where we have 2 moles of SO2G reacting with O2G forming 2 moles of SO3G. So this is Kp1 and SO3 converting into SO2G and half moles of O2G forming Kp2. Okay, so in this case we can write Kp1 as partial pressure of SO3 squared divided by partial pressure of SO2 squared multiplied with partial pressure of O2, and Kp2 can be written as partial pressure of SO2 multiplied with partial pressure of O2 to the power half divided by partial pressure of SO3. So this is nothing but Kp2 is 1 upon root of Kp1. So this is the relation between these two equilibrium constants. Now another interesting topic is, what if the reaction takes place in multiple steps? Reaction takes place in multi-steps or multiple steps. So in this case we can simply write that, suppose we have 2 moles of H2G first reacting with, or rather let's be abstract, so we can write that 2Hg getting reacted with Bg forming 2Cg plus Dg, and this is Kp suppose, and the step 1 for the reaction was Ag plus Bg getting converted into Cg plus Eg. This is at Kp1, and step 2 would be Ag plus, it reacts with the products from the previous reaction, forms Cg again plus Dg. So this is Kp2. So overall reaction would be the above one, and in this case we can write Kp1 as partial pressure of C into partial pressure of D, or E rather, divided by partial pressure of A into partial pressure of B, and Kp2 would be partial pressure of C, partial pressure of D divided by partial pressure of A and partial pressure of E, and Kp instead can be written as partial pressure of C squared partial pressure of D divided by partial pressure of A squared into partial pressure of B. So how can we derive Kp from Kp1 and Kp2? I think if you just multiply Kp1 with Kp2, Pc squared would be there, then Pe would be getting cancelled out from each other, not writing it. Okay, so Pd would be there divided by, again Pa squared would be here and Pb would be here. This is nothing but Kp1 multiplied with Kp2. Okay, so with this we come to the end of this lecture. In the next lecture we will be seeing more on the equilibrium constants. So till then, good luck and goodbye.